Our first speaker is Hao Wu from Tsinghua University, and the title is Connection Probability for Loop ON Models and BPZ Equation. Welcome.
好，因为听众在线下的听众都是中国人，所以我就直接切换成中文了。好，我们这个报告最关注的这个核心的模型是这个 Loop ON Model。那么 Loop ON Model 的定义呢，其实非常简单。我举一个特殊的例子，比方说它是对任何一个图都是可以定义的。然后我举的特殊的例子呢，就是说我们对这个 honeycomb lattice 或 hexagonal lattice 就六边形网格定义这个模型。那么对于六边形网格呢，那每一条边是开着或者是关着。那么这个模型呢，它有两个参数，一个是 p， 我们管它叫做 edge weight， 还有一个是 n， 叫做 loop weight。那么最后这个模型就是你取好一个这个 configuration omega 之后呢，这个 omega 出现的概率呢是正比于 p 的这个 o omega 次方 ，o omega 是数这个 omega 里面有多少开着的边，然后乘以 n 的 l omega 次方。这个 L 呢是数这个 configuration omega 里面一共有多少个 loop 的数目，所以这是它的定义。好，那么这个模型定义好以后呢，事实上做这个物理上面发现这个模型它是有 phase transition 的，就这个模型本身是当然是会依赖于这个参数 n 和参数 p 的选取。当这个 n 在0到2之间的时候呢，会存在一个critical PC， 一个临界的 PC， 这个 PCN 呢，它是 n 的一个函数，就是现在看到的这个方程。那么这个 critical 的意思呢是说，如果 P 小于 PC， 也就是说相对来说开着的边比较少，那么这个模型是次临界态。次临界态我们可以认为就是你可以去算这个点和点之间的这个连接的这个概率，这个概率的衰减是指数衰减，这是次临界态。那么这个模型比较有意思的呢是，除了次临界态以外，它有两个临界态。第一个临界态呢是 P 刚好等于 PC 的时候，这个时候是一个临界态。然后这个临界态呢，事实上是猜想是说，这个临界态在取这个尺度极限就 scaling limit 以后呢，它的极限是共形不变的。共形不变得到的这个结果就是这个极限呢，它是一个稀疏态 dilute phase。然后相应的话呢，如果你知道这个 SLE 的语言的话，它跟 SLE kappa 里面这个 kappa 的对应呢 ，kappa 是在8/3到4之间，这个 kappa 和 n 呢之间是这样的一个关系。好，那么 p 大于 pc 的时候，它也是一个临界态，这个实际上跟我们一般的模型是不一样的，就是其他的模型是说 p 大于 pc 是超临界态，但是这个 ON loop model p 大于 pc 的时候，它仍然是临界态。然后这个临界态的时候，这个临界态呢，人物理上的猜测是说，这个东西这个时候它也是临界态，就对所有的 p 大于 pc 是临界态，而且只要 p 大于 pc， 然后它的极限都是一样的，就它不再依赖于 p 了。然后得到的极限呢，是我们说的这个稠密的临界态，是dense critical phase。其中呢，这个 kappa 和 n 呢，也是满足这样的一个方程，只不过 kappa 的取值范围呢，从8/3到4变成了4到8之间。好，这是有关 ON loop model 的一个猜想。在这个猜想呢，这是我们这个左边这张图呢，实际上就是刚才画的这个 ON loop model 猜想的这个一个 phase diagram 一个像图，它的横轴是 n， 纵轴是 p， 然后蓝色的这条线就是我们刚刚看到的这个 PCN 的这个函数，所以它这个随着 n 从0到2的话呢，它这个取值呢从1除以根号下2加根号2，然后变到了取值是当 n 等于2的时候，它是1除以根号2。然后黄色这条线呢，事实上也是它的一个critical line。然后，但是这个 critical line 呢，在物理上或者说在数学上，或者跟我们这个报告的话呢，它关系不是特别紧密。然后总之呢，这个猜想是说，只要 p 严格在这个蓝色这条线以上，它最后取极限的都是临界态，并且取完极限是一样的，是跟 p 无关的。虽然这个整个在这个 PC 之上呢，它的极限跟 p 是无关的。但是这个黄色曲线上的这些模型呢，比这个其他地方的模型要更好一点。在物理上面说，如果你去考察这个 higher order correction 的话，黄色这条线的 higher order correction 的 leading order 会消失，所以可能分析起来会更方便一些。当然这一部分的话呢，是跟我们这个报告是没有关系的。好，那么在这个猜想里面呢，我们可以看到n 和 kappa 之间是满足这样的一个关系，就 n 等于-2倍的 cosine 4派除以 kappa， n 的取值范围是在0到2之间。所以如果我们去反解 kappa 的话，其实 kappa 会有很多个取值，然后我们这儿呢会出现2个区间里面的取值 ，p 等于 pc 的时候是 kappa 在8/3到4之间。p 大于 pc 的时候呢，这个 kappa 的取值呢是在4到8之间。那么这2个值如果对应同一个 n 的话，我们会发现它们俩之间的关系呢是这个 kappa 分之一加上 kappa hat 分之一等于1/2。这个事实上是这个领域里面很有名的一个猜想，就是说当你这个 kappa 和 kappa hat 在这个2个区间范围内取值，并且满足这样的一个关系的时候，它们对应的 n 是同一个 n。也就是说，一个对应的 open loop model 的稀疏态，一个对应的是重密态。那么对于这一个猜想里面，事实上最有名的一个猜想呢是说，我们考察这个经典的一星模型。通常我们知道，这个如果是一星模型是这个 critical 的时候，它是有共性不变的。那么待会儿我们也会看到相应的结论。然后，但是如果我们考察的不是 critical， 而是 high temperature easing， 实际上物理上一直在猜想的，如果你考察的是 high temperature easing， 就是超高温度高于临界温度的时候，它的这个取极限以后所在的这个 universality class， 就是它的叫什么？这个取极限以后对应的这个 universality class 跟这个渗流模型对应的 universality class 是一样的。然后也就是说，如果你考察的不是临界的一星，而是高温的一星的话，然后你去考察同样的，比方说 SLE 的收敛的话，那它相应收敛的极限应该是 SLE6，应该跟渗流是一样的。那特别的回到我们这个关系式里面，我们可以看到1/3加上1/6等于1/2。所以这一个猜想呢，事实上是这整个这个猜想中的一个特例，就是一星和渗流模型是可以用这样的一个关系对偶起来。好，那么这个是有关 loop ON 模型的一个猜想。那么我们看一下这个猜想里面哪些是已经知道了。事实上，这个猜想被严格证明的这几个情况呢，我也标在这张图里面了。那么已经严格在这个 ON loop model 里面严格已经知道它确实是共性不变的呢，是这样的4个模型。第一个模型呢是 n 等于0 p 等于1，是在这个点。这个点对应的模型呢是 uniform spanning tree 均匀生成树。那么这个模型呢，它确实是共性不变的，这个是由 Lawler、Schramm 和 Werner 在2000年左右证出来的。下一个模型呢是 n 等于1 p 等于1，是这个位置。这个对应的模型呢是渗流模型，它也确实是共性不变的，这个是 Smirnov 在2000年左右证出来的。再下一个模型呢是 n 等于1 p 等于1除以根号3，这个是这个地方，这儿事实上对应的就是 critical easing 模型，经典的这个临界easing模型。第4个模型呢是 n 等于根号2 p 等于1，实际上这个对应的模型呢叫 FK easing 模型，或者叫 random cluster model， 对应里面的 cluster weight 是等于2的这个模型。这个模型呢和就是 FK easing 模型和 easing 模型是为对偶的模型。那么这2个模型呢，事实上是在同一个系列工作里面证明它们是共性不变的。好，那么所以对于这个猜想而言呢，这个猜想是整个对这个所有这些 p 等于 pc 和 p 大于 pc 提出的猜想。到目前为止，我们可以证出来的真正共性不变的呢，只有4个离散的点。好，那么这个是 loop ON model 相关的猜想和我们已经知道的一个，就是4个模型已经知道它确实是共性不变了。好，那么我的这个报告里边感兴趣的问题呢，感兴趣的就从题目我们可以看到，我感兴趣的问题是我们要在一个多边形里面 polygon 里面考察这个 loop ON model， 然后我要去算它的连通概率。那么这个是什么意思？首先呢，我们这儿画了一张图，这张图呢是一个6边形，一个很大的6边形，或者说你可以认为它是这个6边形网格，就是 hexagonal lattice 的一个子图，然后它呢是一个单连通图，然后在这个图上面呢，我标记好6个边界点，就这6个边界点我把它事先取定好了 ，x1 一直到 x6。那么这6个边界点呢，把我这个多边形的边界呢分成了6段。好，那下面我来定义我这个模型的边界值。边界值说的是呢，从 x1 到 x2 上的边呢，我全都让它开着。2到3我不管，就是说我说它是 free 的。3到4全部开着，4到5是 free 的，5到6是全部开着，6到1是 free 的。这是我取定的一个边界值。好，那么对于这个多边形内部的这些边，我就按照这个 loop ON model 的概率去给它做这个，给它定义它的测度。好，那么定义好这个 loop ON model 以后呢，我们可以看到我关心的问题是 从 x1 到 x6这6个点之间呢，事实上是会被这个 ON loop model 里面的这些loop 或者说这些曲线给连通。那么6个点之间的连通呢，就是构成了这个点对之间的一个划分，构成了5种可能性，就是我们现在看到的下面这5种可能性。就是6个点对两两之间的这个平面划分呢，一共有5种可能性，这是 Catalan number 格。然后那么刚好6个点的时候呢，刚好就是5种可能性。那么我现在想问的问题呢，就是这5种可能性每一种可能性出现的概率是多少？好，那么这个问题的答案呢是这样，在物理上面给了这样的一个猜测。那么这个猜测是说，如果我们考察的是刚才我说的这个 critical loop ON model， 这个 n 的取值呢是在0到2之间，然后 kappa 的取值呢是在8/3到8之间，就是刚才让它俩之间的关系就是我们刚才看到的这个关系 n 等于-2倍的 cosine 4派除以 kappa。那么我要去算这样的我上面说到的这个概率，那么这个概率呢，在这个网格的尺度局限趋于0的过程中呢，这个概率会收敛，它会收敛到一个极限。那么这个极限呢，是我们现在看到的这个猜想这个公式的右手边的这样的一个函数。那么右手边这个函数里面有3个量，第一个量呢我们叫做 mean matrix， 待会儿我会把这3个量的定义一一写下来。第二个量呢，这个分母 f 贝塔我们叫它 Coulomb gas integral。第3个量这个分子 z alpha 我们叫做 pure partition function。从这个名字我们就已经可以看到它是跟这个 CFT 里面的 correlation function 有关的。好，下面我就来一一的介绍一下这3个东西都是什么。第一个 mean matrix。mean matrix 的定义很简单，然后它的出发点呢是说，我有一个阿尔法一个贝塔，阿尔法和贝塔全部都是这个2n 个点对之间的一个平面点对划分，一个是阿尔法，一个是贝塔，我把它放在上面平面画好。画好以后呢，我把这个贝塔关于这个时轴转到下半平面，然后放到阿尔法的下面来，就变成了最后这张图。这张图呢，我们管它叫做这个阿尔法和贝塔之间构成的一个 meander。对于这样的一个 meander呢，我们可以看到这个 meander 里面就有若干个 loop， 然后在这个例子里面刚好有一个，当然你也可以画出有多个 loop 的这种情况。然后呢，对于这个 meander 呢，我要数这个 meander 里面有多少个 loop， 把这个数数好了以后呢，我的这个 meander matrix 呢，它的定义，它的每一个 entry， 它的 entry 是由这个阿尔法和贝塔标记的，所以这个矩阵呢，它其实非常大，它的矩阵的尺寸是这个 Catalan number 乘以 Catalan number 格。然后每一个这个点上的在阿尔法贝塔处的取值呢，这个取值的数呢是 n 的一个若干次方，这个次方就是你刚才在这个阿尔法贝塔里面数这个 mean 的里面有多少个 loop， 就是这样的一个数。这是我们定义的这个 mean matrix。那么这个 mean matrix 呢，如果你对表示论比较熟悉的话，实际上这个东西在表示论里边是一个已经研究的非常清楚的一个数学对象。那么对于这个 mean matrix 呢，它的信息其实已经搞得非常清楚了。然后有一个性质是我们这个报告里边比较相关的，就是这个矩阵，这是一个非常非常大的矩阵，这个矩阵到底什么时候是可逆的？然后这件事情呢，事实上已经非常清楚了，在1997年的时候，这几位物理学家就已经搞清楚这样的一个矩阵到底什么时候可逆。它可逆当且仅当呢，这个 kappa 是在这样的一个范围内，也就是说 kappa 在0到8之间，但是要除掉一些点。这些点呢是长成4p 除以 p 撇这种形式的这些点，要除掉这些点，就是它刚好在这些点上的时候是不可逆的。事实上，这篇文章实际上算了这个 mean matrix 的行列式是什么，然后把这个行列式解出来以后，发现这个行列式它的零点是这些点。是的，是的，待会儿我们会看到这个 minimum model 里面那些参数，就是那个 p 和 p 撇。好，那么事实上它这篇文章里面呢是算了这个 mean matrix 的行列式，然后把这个行列式它就已经完整的算出来。算完以后呢，当然是发现在kappa取这些值的时候，这个行列式刚好是0，所以它是不可逆的。所以它可逆当且仅当你要除掉这些点。好，那么我们可以在这儿对，这是这个 mean matrix 跟我们这个报告相关的，就是我们其实知道它什么时候可逆，什么时候不可逆，这是第一个概念。第二个概念是这个 Coulomb gas integral， 所以你从这个名字可以看到，反正它就是一个很大的积分。那么这个积分长成什么样子呢？首先呢，它有一个积分线，这个积分线的定义是这样的，就是首先我们这个 Coulomb gas integral 里面有一个下标贝塔，这个贝塔呢事实上是对应的这个2n个点之间的一个点对划分。 然后我把这个1到 2n 这个点对划分呢，按照一个指定的顺序把它排好，就是 A1 和 B1 是一对儿 ，A2 和 B2 是一对儿，然后把它们排列好，然后并且呢 A 在 B 前面，然后并且 A 是一个单调增的关系，就是我先把这个点对划分呢按照这样的一个顺序排列好。好，那接着我来定义我的这个积分。那么这个积分的积分线呢，它一共有 n 个积分变量，然后 U1 呢是从 xa 积到 xb1，UN 呢是从 xan 积到 xbn。然后这个被积函数呢，其实长得是比较简单的。这个被积函数其实就是个多项式 ，us 减 ur 的一个若干次方，然后乘以 ur 减 xi 的若干次方。所以这个被积函数其实长得是很简单的。然后前面呢，这儿有一个跟 x 有关的，这个函数是很简单的，这个跟积分是没有关系的。然后最前面呢还有一个归一化的常数 c 的 n 次方，所以这个 c 是一个显示的一个常数。当然这个 c 我没有写在这个 PPT 里面。但它就是一个显示的常数，它的作用就只是一个归一化常数而已。好，那么这是这个积分的定义。那么接着我们来看一下这个被积函数。这个被积函数呢是长成表 ur 减 xi 的若干次方。但是这儿呢我们可以看到这个 ur 的积分线是在这些范围内，所以这个 ur 有可能是比 xi 要小的。所以这个被积函数本身它其实是一个赋值函数，它不一定是一个实质函数。所以它这个被积函数是赋值的，其实我们在这儿做积分的时候就要说清楚，那你这个被积函数的，你到底是选的哪一个 branch 去拿它去做积分？好，那我们这儿选的这个积分的这个 branch 呢是这样选取的，就是这个被积函数呢它是赋值的，然后我现在可以取定一个一定范围内让它的取值为正，就是在这个范围内让它取值为正。然后为什么我要让它取值为正呢？事实上，因为我们最终的目的是要证明这个东西会给一个概率。然后它既然会给你一个概率，它起码得是正的，不然的话它就没法定义成一个概率。对，都是整数，从1到 2n 的一个1到 2n 的一个整数的排列。对，好，我们的被积函数呢是赋值的，然后我把被积函数的具体的分支呢取成这样子。这样的一个取法呢，事实上就是保证这个被积函数尽量是正的，因为我最后其实希望被积出来以后的这个函数是正的，因为最终我要证明这样的一个函数会给我一个概率的表达，所以它最好是正的，不然的话不然它是不可能给我一个概率的。好，那么这个是这个被积函数的问题。那么最后再来看一下这些积分线。这些积分线呢，事实上我是虽然这儿写的是从 x1a1 积到 xb1，但其实这个积分线呢，事实上是在这个就是围绕着 xar 和 xbr 的这个 Coulomb contour 上面做积分，所以它其实是这个积分线本身也是这个辅平面上的一个环路。然后这个环路的选取的好处呢，是这个它绕着每一个点 xar 或者 xbr。它是正向转一圈，逆向转一圈，这是它的好处，所以它其实是比较好去定义这个积分的。好，那么这个是 Coulomb gas 积分的这个定义，所以大家记住的就是说，反正它就是个积分。然后在这个积分里面呢，我们可以看到有这个东西 ，ur 减掉 xi 的负4除以kappa 次方。所以这儿我们可以看到，如果这个 kappa 是严格大于4的，那么这个 exponent 就会是小于-1的。那它这个时候其实在这个环路上的积分，实际上是可以写成线积分的，因为线积分本身也是收敛的，所以你可以证明它们俩之间只是一个常数倍的关系。但是如果 kappa 小于4的话，这个东西的线积分就没法定义了，就是你把它真的记成这个从 x1 到 xa 到 xb 的积分呢，它就爆炸了。那这个时候我们就只能把它理解成在这个 Coulomb contour 上做积分。Okay, sure. Yeah, because at the beginning all the audience are Chinese, so I switched to Chinese. Okay, so then let's switch to English. Okay, so this is the definition of the Coulomb gas integral. So by the definition, this is just a big integral. The integrand function is this polynomial, so it's us minus ur to a power and ur minus xi to a power. So this integrand function is a complex valued function. And before we do the integration, we have to first figure out what's the branch we choose for this integrand. And the branch is chosen so that we want to make it as positive as possible, because in the end, finally we would like the integrals to be positive. So this is the branch for the choice of the integrand function. And then the integral contour is that we integrate those u variables according to Polygon contour around this marked points. So this Polygon contour is good to analyze because they surround the marked points, positive ones and the negative ones. So it is easier for the analysis. So this is the definition of the Coulomb gas integral, and then why we are interested in this Coulomb gas integral. So in fact, this is not the first function that we are interested. It already appeared in physics literature a very long time ago. So the idea to why we want to study such function is because physicists find the representation theory of the thorough algebra will give us explicit formula for BPZ equation in conformal field theory. And this Coulomb gas integral is a particular example of explicit solution to this BPZ equation. So this is the BPZ equation in conformal field theory at level 2. Okay, so the idea is that they find this ansatz satisfy this PDE equation. So this is the reason why we want to understand this Coulomb gas integral. Okay, so for those Coulomb gas integral, so we know a lot of properties of them. So first of all, as I said before, we would like those functions to be positive because in the end, we want to show that they give us some probability. So the first question is whether they are positive or not. And the answer is the following. So in fact, those Coulomb gas integral, they are positive when kappa between a thirds and 8. And at the two terminal values, a thirds and 8, in fact, they vanish. On top of that, we even know how fast they vanish. We know how to renormalize them in order to get a positive limit. So in fact, when kappa goes to a thirds, we know that this function will tend to 0 at a rate kappa minus a thirds to the power 1. And when kappa goes to 8, this function will tend to 0 at rate 8 minus kappa to the power n, so with different power. So we know that at these two terminal values, this integral function will vanish, and we even know how to renormalize them. Okay, so this is in this interval, and for kappa less than a third, in fact, those functions can be negative. We also have an analysis of the 0 points of this function when kappa goes to 0. So originally, we want to introduce this function as positive as possible, but in the end, the best we can do is that for kappa between a thirds and 8, they are always positive. But for kappa less than a thirds, we can't avoid the case that they can be negative. And there we can also even describe the 0 points of these functions. Okay, this is the Coulomb gas integral. And the third quantity in this conjecture is called the pure partition functions. So by definition, the pure partition function is a collection of smooth functions satisfies the same BPZ equation. So this is another system of solutions to the BPZ equation. And for this system of the solution, we require a particular boundary value for those functions. So this boundary value is we call asymptotic. So it says that when 2 points xj, 2 neighboring points xj and xj plus 1 are very close to each other, we require this function to explode at a certain rate. And after when normalized by the explosion, we require that it converge to the function that with these 2 points removed. So this is the requirement. So you can view that this is a system of the PDE equations, and this is a sort of boundary value problem. So now you can ask whether the function satisfying your definition exists and is unique. And the answer is that, yes, this is true. So the collection of pure partition functions exists and is unique for all kappa between 0 and 8. But the full answer to this question involves 6 papers. The first answer to this question is about the uniqueness of the solution. So for the uniqueness of the solution, Floha and Cleveland proved in a series of 4 papers in CMP in 2015 that so if the solution to the system exists, then they are essentially unique. And then for the existence, in fact, it took a pretty long history. So at the beginning, so first, Peltola and Peltola constructed the solution to the system for irrational kappa, so for kappa between 0 and 8, but remove all rational numbers. And recall that all the models we are interested in are rational kappa. So first they construct a solution, but the solution is not sufficient for our purpose because all the kappa we are interested are rational. And then there are several different papers about the existence of the pure partition functions. And then in the end, so far, so we can say that the function exists, and it exists for all kappa between 0 and 8. LP, this is the link planar link pattern. Yes. Okay. Yeah. So this is the existence and the uniqueness of the pure partition functions. And here are a few properties of those functions. So first of all, in fact, this collection of pure partition functions, we can prove through the boundary value that they are linearly independent. In fact, we can show that this collection of functions, so the total number of the solutions here is Catalan number. So this Catalan number solutions form a basis for the solution space of the second order BPZ equations. And the pure partition functions, they are all positive. For all kappa between 0 and 8, they are always positive. And next, when kappa tends to 8, it tends to 0. And we even know how what is the decaying rate. So decaying rate is kappa 8 minus kappa to the power n minus 1. So not n, so this is n minus 1. So in contrast to this polynomial decay, in fact, we also know that when kappa goes to 0, the pure partition function explodes exponentially fast when kappa goes to 0. But when kappa goes to 8, it decays polynomial in kappa. So this is these two terminal values has very different behavior in terms of the pure partition functions. Okay, and now let us come back to the Coulomb gas integral and the pure partition function. So in the definition, we already see that both of these two families of functions are solution to the BPZ equations. And we also know that the pure partition function Z alpha give a basis for the solution space. And the Coulomb gas integral is a solution. So then we know that this solution Coulomb gas integral can be written as a linear combination of the bases. And this linear combination is given exactly by this meander matrix. So this is how these three quantities are connected together. And here, in fact, this relation extends to all kappa between 0 and 8. And even we see that when kappa less than a third, this parameter n can be negative. So this linear combination is even true when its coefficient can be negative. So this is why this Coulomb gas can be negative. Okay, so just a summary of the properties of these two collections of solution. So first, we know that pure partition functions are always positive, and they are linearly independent, and they form a basis for the solution space. And for the Coulomb gas, then we want to understand whether they are positive and whether they are linearly independent. And now this is also known. So they are positive when kappa between a thirds and 8, but they can be negative when kappa less than a thirds. And also we know that this Coulomb gas integral, they are linearly independent if and only if this meander matrix is invertible. Because this Z alpha, they are linearly independent. And for this matrix, we know whether they are invertible or not. So they are invertible if and only if kappa is between 0 and 8 and remove these particular values. Okay, so this is the connection between the Coulomb gas integral and the pure partition functions. Now we can go back to this conjecture. So this conjecture says that for each boundary value data, and for each internal link pattern alpha, we want to calculate what is the probability of this loop Owen model to form a link pattern alpha. And this probability is given by the product of the three quantities. This is the meander matrix. This is a pure partition function, and this is Coulomb gas integral. And in the previous page, we already see that if we summing over all possible alpha, they are related in this way. So here we translate this function to here is that we summing over all possible alpha, it sum up to 1. So it makes this conjecture then makes more sense. Okay, so this is the conjecture for the loop Owen model. And in fact, we already say that for this loop Owen model, we already know 4 of these models are conformally invariant. And for all these 4 models, we can also prove that this conjecture is true. So for uniform spanning tree, this conjecture is true. For percolation, this conjecture is also true. For FK easing model, this is also proved. And for the critical easing model, so this conjecture is also true. Here I put two particular functions in these four models. The first particular function is for percolation. So when n equals 1 and p equals 1, this is the famous percolation model. In this percolation model, the Coulomb gas integral is very special because this Coulomb gas integral when kappa equals 6, it is always 1. So it is independent of x. It is independent of beta. So this is, in fact, this is consistent with the well-known fact that for percolation, it is independent of the boundary data. And another particular function is for the easing model. So if you write down this Coulomb gas integral and set kappa equals 3 in the formula, you find that this Coulomb gas integral when kappa equals 3 has a Pfaffian expression of the boundary points x1 to x2n. And in fact, this Pfaffian comes from the fermion of the easing model. And in this formula, we also see that in the right-hand side, it has nothing to do with beta. So it is only a function of x, and it is independent of beta. And this is also consistent with the known result that this percolation and the easing, that in the same, the fugacity, both of the fugacity equals 1. So both of them have n equals 1. So in this sense, we already see that in this formula, if you put n equals 1, so this coefficient is always 1, then the right-hand side has nothing to do with beta. So therefore, the left-hand side has nothing to do with beta. So this is the very particular case for percolation and the easing. So this is also another perspective of the conjecture, that why this percolation is conjectured to be in the same universality clause for the high-temperature easing model. Okay, so the proof for these four models, the basic strategy is exactly the same. So there are three-step proof in the proofs. The first step is that we need to identify the limit of our allomorphic observable. Second step, we need to solve from the allomorphic observable. We need to solve the law of the interface and derive that it is a Loebner chain driving function associated to the Coulomb gas integral. And the last step is that once we know the second step, in fact, we can show that this Z alpha over F beta will give us a martingale, and then we need a refined analysis of this martingale, and then use optional stopping theorem to calculate the probability. So we will see this strategy in a more concrete example in the second part of the talk. Okay, so this is the conjectured loophole model for the connection probability, and this is the already known result. Okay, so now I will show some connection of the Coulomb gas integral to correlation functions in conformal field theory. So this connection is called Frobenius series expansion. So here the idea is that when we consider our Coulomb gas integral, so they are a function of the two variables from x1 to x2n. So as a function in these variables x1 to x2, so now we want to understand if x1 and x2 are very close to each other, how does this function explode or tend to 0? So what is the asymptotic if we view it as a function in x1 and x2? And the conclusion is that, so if we expand this function as a series in x1 and x2, then the leading order of this series is x1 minus x2 minus x1 to the power 1 minus 6 over kappa. So this is the usual leading term. The sub-leading term, so if you remove this leading term, then the sub-leading term is x2 minus x1 to the power 2 over kappa. And there's some particular case that we even see a logarithmic correction between the leading term and the sub-leading term. So this is a summary of the expansion. And now I will give the concrete conclusion one by one. So the concrete conclusion is that for kappa between 8 and 8, this is what we call generic case in this open interval. And we consider as x1, x2 are shrinking together, what's the Taylor expansion of those Coulomb gas integral. And the conclusion is that the leading order is x2 minus x1 to this power 1 minus 6 over kappa with an explicit coefficient here. This is the leading order. And the sub-leading order is x2 minus x1 to the power 2 over kappa with an explicit coefficient. And this is the remaining term. And this is this expansion. So why we are interested in this kind of the expansion? So basically, you can just think this is a Taylor expansion of the function. And the idea and the reason why we are interested in this expansion expansion is that we want to compare what is going on for this Coulomb gas integral and correlation function in conformal field theory. So from the conformal field theory, if you believe all these models are related to some CFT, and if you understand those operators in the CFT properly, you can take operator product expansion of the field. And then we want to argue that, in fact, this Coulomb gas integral is related to the degenerate field of level 2, this phi 1, 2. And we compare the OPE expansion of phi 1, 2. So this, in physics, they predict that this OPE expansion of the phi 1, 2 has exactly the leading order of this, the same order here, and the sub-leading order is the same level here. And here the notation phi 1, 1 is the identity field, phi 1, 2 is the degenerate field of level 2, and the phi 1, 3 is the degenerate field of level 3. And here the exponent 1 minus 6 over kappa and 2 over kappa. In fact, they are related to the conformal field, conformal weight in this way. So this 1 minus 6 over kappa is h11 minus 2 h12. 2 over kappa is h13 minus 2 h12. So therefore, in fact, our calculation is consistent with the OPE expansion of the CFT field phi 1, 2. So this is the generic case. And for this two terminal value for kappa equals a thirds and kappa equals 8. So in fact, these two values are more interesting. For kappa equals 8, we want to do the same thing. But then we've realized that, in fact, between the leading term, so the leading term, the exponent is minus 5 over 3. The sub-leading term exponent is 3 over 4. And between the leading term and the sub-leading term, in fact, there's a tricky term between the leading term and the sub-leading term. This tricky term is called, we have a logarithmic correction for the sub-leading term. So the second term, in fact, it is there is a logarithmic correction, and we also know how to calculate this coefficient explicitly. And this is also consistent with the OPE operator product expansion of the of the field of phi 1, 2 at this particular value. In fact, in physics, they conjecture that this field corresponding to this kappa is logarithmic CFT. So they're not the usual minimal model. So there's a logarithmic correction. But the question is where you can see this logarithmic correction. So here we provide one example where you can see this logarithmic correction. So you can see this logarithmic correction in the Frobenius series expansion. Okay, so this is the case when kappa equals a thirds. And another case when kappa equals 8, we also see logarithmic correction. But here we see logarithmic correction much earlier. So there is already logarithmic correction in the leading order. So leading order, there is already logarithmic correction. And this is also consistent with the OPE expansion of the field when kappa equals 8. Okay, so this is why we want to understand this Frobenius series expansion. So we want to compare the Coulomb gas integral with the correlation field in the conformal field theory. Okay, so now the last part of the talk is we'll focus on this case, kappa equals 8. Because in this case, we see that we can find this logarithmic correction in the very early order. So this provide some hint that it will be easier to analyze this model than another one in order to see the logarithmic correction. Okay, and the third part, I will focus on this the last case, UST, so for kappa equals 8. So in fact, this UST model is already an interesting model in its own. So you can see it as a particular model in this Owen loop model, but we can also repeat its definition for its own. So for a uniform spanning tree, it can be defined for any finite connected graph. A tree is a subgraph of G without loops. So this is definition of a tree. A spanning tree is a tree that it covers all the vertices. And uniform spanning tree is a probability measure that each spanning tree is chosen uniformly. So this is the definition of uniform spanning tree. And now we are interested in a uniform spanning tree in a polygon. Here are two examples. The first example is we consider a uniform spanning tree in a polygon with two marked points on the boundary. So it's a polygon of two marked points, A and B. And our boundary condition is that for all the edges from A to B on the boundary, they are always wired. And for the edges between B to A, we don't say anything, so they are free. So this is what we call diversion boundary condition for the uniform spanning tree. And for the inside, we just choose this spanning tree uniformly. And then after we define this uniform spanning tree with diversion boundary condition, we see that we can draw this orange curve between this tree and this dual tree. So it's a curve staying between the tree and the dual tree, and it starts from A and ends all the way to B. So in the discrete level, we already see that this curve is a piano curve, so it visits all the vertices. So this is an example when we consider uniform spanning tree in a polygon with two marked points. Here is a uniform spanning tree with a 6 marked point on the boundary. So x1 to x6, they are all marked points on the boundary of my polygon. And my boundary condition is alternating. So all the edges from 1 to 2 are wired, from 2 to 3 are free. So they are alternating, go all the way to 6. And then for the inside, which is the sample of our uniform spanning tree measure. And then after we sample the tree, we see that there are 3 piano curves connecting among this x1 to x6. And these are 3 curves, so they are purple, green, and orange. They form a planar link partition between the 6 marked points. So this is an example of 8 marked points. And now my question is, so first I sample my uniform spanning tree in this polygon. And then I fix certain boundary condition. So boundary condition is also a planar link pattern. And for the inside of the polygon, I just sample my model uniformly. I choose a uniform spanning tree model. And then I draw the connectivity pattern between these colored curves. So the blue curve gives the connectivity pattern of the boundary data. This red curve gives the connectivity between for the inside of the polygon. And now I want to ask for each outside boundary condition data and each internal link pattern, what is the probability for the uniform spanning tree to form such a probability? And now the answer is this. So we know that the scaling limit of such connection probabilities is given by these 3 quantities. So this is exactly the same 3 quantities as we see for the loop ON model, but each of them have to be renormalized because all the 3 quantities will tend to 0 as kappa goes to 8. But for all of them, we know how to renormalize in order to have a positive limit. So after we renormalize the 3 quantities properly, then we get a positive limit, and this positive limit will give exactly the answer to this question. So here the matrix is called the renormalized mean matrix. The Coulomb gas is the renormalized Coulomb gas, and the pure partition function is also renormalized. For all the 3 quantities, we know that all of them tend to 0 as kappa goes to 8, but we know how they tend the decaying rate. So we normalize them properly by the decaying rate and in order to have a positive limit. So this is the answer to this question. So in fact, for the left-hand side, for the probability in the left-hand side, there are already works on this probability. In particular, in the second work by Ken and Wilson, they provide a systematic way to calculate the probability in the left-hand side. So, but when we check this paper, in fact, we don't know how to check that their answer is the same as this one. So we only know that their answer is the same as this one after we prove this formula. Okay, so this is the answer to the uniform spanning tree. And now I give a few words on the strategy of the proof. So the proof is exactly the same steps as before. So the first step is that we need to identify the limits of the holomorphic observable. Here, in fact, this first step is the most tricky part of the conclusion. In the uniform spanning tree, so in the first line here, they are just a uniform spanning tree in this polygon with different boundary conditions. And then on top of those discrete models, we realize that we can construct allomorphic observable, and this allomorphic observable have a very good limit. And this limit is exactly the conformal map from the polygon on top line to the polygon on the bottom line. So the polygon in the bottom line is a rectangle with a certain horizontal or vertical slit. So this is the limit of those allomorphic observable. Here is one concrete formula. So this is the Schwarz-Christoffel formula for this kind of conformal maps. Yeah. Okay, so in fact, this is the most tricky part of the proof. So after we identify these allomorphic observables, then we try to solve the driving function from the allomorphic observable. And then we realize that this driving function can be given by this Coulomb-Gas integral. After we know that the driving function is related by the Coulomb-Gas integral, and then we know that this Z alpha over F beta will give us certain martingale. And then we need a very refined analysis of this martingales to show and apply optional stopping theorem to calculate the probability. So this is the general strategy. And for the UST model, the good thing is that in fact we have a very concrete description of those allomorphic observable. Okay, so now let us go back to logarithmic CFT. So in the previous page, we already see that this Coulomb-Gas integral is related to the probability for the uniform spanning tree. And for those Coulomb-Gas integral, we can also calculate their Frobenius series expansion. And for the Frobenius series expansion, we see that there is a logarithmic correction in the leading order. And now, in fact, our future work of the direction is the direction of the future work is that we already have many physics literature about the logarithmic correction of logarithmic CFT for the uniform spanning tree. For instance, we can compare the OPE expansion with our Coulomb-Gas integral. They are consistent. However, we don't know how to directly relate our Coulomb-Gas integral to those operators in the conformal field theory. And also for those operators in the conformal field theory, in fact, there are many candidates for the operators. Some of the one thing we find that might be interesting is that our allomorphic observable should relate to some operator to the CFT. So this is the direction of our future research. Okay, and also by the way, so this is the UST model is conjectured to related to logarithmic CFT with central charge C equals -2. So this central charge is already negative. Okay, so this is all the related to the works of me related to this talk. Okay, thank you for your attention.
Thank you, Professor Wu. So any question or comment?
Is there any intuition about the two numbers 8 over 3 and 8?
Yeah, yeah. Okay, so this 8 over 3 and 8. So they are if we go back to the own-loop model, so they are the terminal values for this own-loop model at these two intervals. So they are very special in many sense. So one sense is that when kappa goes to these two values, in fact, this own-loop model will converge to uniform spanning tree and self-avoiding walk. And these two models are already very different from the other ones because when n goes this means that n is 0 at those 2 points. So there you already need to do some renormalization. So this is very different from positive n. And the second, for the SLE mode, so this 8 is very special because this is the phase transition for this parameter kappa that when kappa beyond 8, the curve becomes space fading. So it's very different from kappa less than 8 case. So usually most of our model is all the kappa all the way up to 8. So we don't do analysis beyond 8. Yeah. So all these models, so this n equals 1 and n equals square root of 2, they are not invertible. Yeah. Yeah. So only n equals 0, this renormalized meander matrix is invertible. But in all these three cases, they are not invertible. Yeah, in fact, so far all the precise known result is about when the matrix is not invertible. Yeah. So here, so in this third part, so I already write that this is related to the minimum model of M21. So this 2,1, this 2 parameter is exactly the parameter of the minimum model for PP prime. Yeah, so the physics conjecture is that in fact for all the loop ON model, they are all related to logarithmic CFT. Just for those two terminal values for kappa equals 8 and 8, we easily see this logarithmic correction in terms of the Coulomb gas integral. And for other model, for instance, for kappa between this interval, so physicists conjecture that this is also related to logarithmic CFT. But so far, we haven't figured out where is this logarithmic yet. Yeah, one of the most famous conjectures about the percolation. So in fact, the percolation is conjecture to related to logarithmic CFT. This is not the minimum model. 4, 3. Yeah, I need to check the index. Yeah, in the very recent. Yeah, I need to check the index. Yeah. So in the recent paper by my student Yu, so he is also one of the co-authors in this paper. So he do find some logarithmic correction for the percolation correlation functions.